All right, here's where we left off with synthetic strategies. So if we've been focusing on this carbonyl group right here, and we'd like to transform it by alkylation, so that's using a Grignard reagent. We have an R group nucleophile. You can also add the nitrile or cyano group to this, Cn minus as nucleophile, cyanide ion. And then we also have this Vidiq reaction where you can add an R group and make this a double bond, C double bond rather than CO double bond. So it's good to study those and be familiar with those so that you can work backwards. So we've only seen one CC bond breaking reaction so far that's brand new, which is the Baeyer-Villiger oxidation. Inserts a peroxy acid's oxygen between a carbon-carbon bond right here, which is sort of alpha to the carbonyl or next to the carbonyl. All right, so we go from aldehyde ketone. I like the functional group approach where you sort of look at how functional groups are changing. So aldehyde ketone to an ester. So when you see that, you know, oh, Baeyer-Villiger oxidation. All right, down here is practice then using different synthetic tools. This is from Klein. Klein's problem was to use only 2 carbon units to make these targets. Mine is to use 4 carbons. Okay, and we'll do one together. My goal is to, starting with only 4 carbon reagents, try to figure out a way to make this. Okay, so I would probably start with the carbonyl version because we've been doing reactions of aldehydes and ketones. And I want to think, how do I turn this into that eventually? This is my target. All right, so from there, I'm thinking back to all those aldehyde ketone reactions we learned, such as imine formation. Okay, so I'm trying to transform this to an imine. So you probably know that you need an amine reagent. So in working forwards then, I know that I need some kind of a nitrogen group, and there's no carbon on this nitrogen other than from the carbonyl group. So I'm thinking maybe I'll use some color to illustrate. This chain here is this chain here. So I really just need this part there. A retrosynthetic analysis, maybe you've been familiar with using a squiggly line just to know those are your pieces. So I need this piece and I need this piece. This is this piece down here. So I need a nitrogen group. So I'm going to use maybe NH3 because there's no methyl or ethyl or any kind of R group on here, up here. So it's just hydrogens. And then I need catalytic acid. I don't want to add so much acid that this is going to be protonated. This has to be my nucleophile. It needs to have the lone pair here. I don't want that to attack there. So I need to only have a catalytic amount, just a little bit of acid to protonate here. So from there, you should be able to picture the mechanism, activation, nucleophilic attack, proton transfer, and you will be able to get to your imine eventually. All right, so the answer to this question is this and this. That's how you make that. Okay, so go through here, and again, maybe use the functional group approach like I did. I thought imine. So that helped me sort of remember what reaction was it that made imines. So same thing with acetals, enamines, hemiacetals, all those things, esters. Okay, so pause it, go back, review the reactions, and see if you can start with a 4 carbon starting material, just like I have here with 2-butanone. Start with whatever 4 carbon unit you need and see if you can piece this together. And by the way, you can't do a ketone here for this one because that's a 5 carbon ketone. So you may need to think of a way to have a smaller ketone or aldehyde and then attach carbons to it, get your 5 carbon chain, and then do a reaction. See if you can figure it out. If you get stuck, just come back to here. All right, so we're back, and this is going to take a while to get used to this requirement of 4 carbons or less. That's just for this particular problem. You don't always have requirements like that. It's just to challenge you to add steps to this process. So on part B, I mentioned there was a 5 carbon chain, so you might need to start with a smaller chain. I would consider starting with a 1, 2, 3 carbon unit and adding 2 carbons as a Grignard reaction, because that's an alkylation reaction. That's this first pathway here. Alkylation. So alkylation means adding carbon groups. So if we alkylate, we need 3-carbon aldehyde, so propanal. We add ethyl magnesium bromide, and then we do acid workup. That makes this an OH group. Then we need to oxidize it back to a carbonyl, so we can do the step where we add the amine. So I use PCC or sodium dichromate in acid, Jones reagent, KMNO4, any of those things. So PCC is fine. And number 4, I need the amine group, which has 2 methyl groups on it. So I do that, but nitrogen makes 3 bonds, so don't forget to add this hydrogen here as well. It gets removed later due to proton transfer. And then H plus, just a catalytic amount, just to get this reaction started, because this carbonyl needs to be activated since dimethylamine is a weak base. So, but I don't want this amine to attack this hydrogen. Remember, I don't want this to get deactivated as a nucleophile. All right, so that's pretty much it. So don't forget, after ethyl magnesium bromide or any Grignard, we usually do an acid workup, either dilute H plus or H2O is fine. Okay, next one is very similar. We have to lengthen the chain. So I chose to have this be my carbonyl group, and then I lengthened it here, because this here would be too many carbons to start with. It's not under 4. Okay, so we have to start with acetaldehyde or ethanal. We add butyl magnesium bromide, so we need 4 carbons added on. Water workup, sodium dichromate and acid is one way to oxidize this, or you can put Jones reagent if you like. Ethylene glycol is going to make my cyclic acetal, just a catalytic amount of acid again. All right, part D, same thing, but this time I'm going to cut it this way, because I have a 4-carbon unit here. I can use that as my carbonyl. All right, same thing though, otherwise. Here, the tricky part is, so cut it here, that's not tricky. Do an acid workup here at the end here. So step 2 should be acid workup. I think I forgot that. Okay, number 2, acid or water workup, just to neutralize that alcohol. Step 3, you want to oxidize it to carbonyl. And then 4, you want to make your imine, but it's a hydroxylated one, so you use hydroxylamine. Again, how do I figure that out? N with an OH group, and then as many hydrogens to make that into a compound, a neutral compound. So NH2OH would be the compound where nitrogen has 3 bonds. Okay, catalytic amount of acid, which of course sometimes we see that in brackets just to emphasize it's a little bit, not stoichiometric. Okay, part F, this one, the key is very similar to part E in its carbon chain. We got to do the same thing at first. But then notice there's a carbon, this part here, we're making an alkene. So this is almost the reverse of oxidative cleavage, where you have an alkene and you oxidize it to carbonyl groups. We're taking a carbonyl and putting it into an alkene. So that's the Vidiq reaction. So for the Vidiq reaction, you need their carbon chain. So I have CH3CH and with a carbanion, and then attached to triphenylphosphine. So I like to show it in its ionic form, but you could also show a double bond between the two if you prefer. Okay, so that's the Vidiq reaction. So you can just put that reagent there. This is called the Ylide, Y-L-I-D-E. All right, and finally the last one is the carboxylic acid, which we haven't really covered very much of, but we've usually been starting with aldehydes and ketones. So what I'm thinking is oxidizing it by inserting an oxygen here, and we did learn how to do that. But to make esters usually, we can also make carboxylic acids, because hydrogen is a better migrator. It will migrate to the oxygen that gets inserted. So that means, and plus you should know that aldehydes oxidize to carboxylic acids. You probably have been learning that a lot with oxidative cleavage. So that should be sort of a natural instinct for you, is to think, oh, aldehydes go to carboxylic acids when they get oxidized. All right, and that's why wine tastes really sour after a while, is the wine aldehydes in wine get oxidized, or alcohol gets oxidized to aldehydes, get oxidized to carboxylic acids. So that's sort of the natural oxidation sequence. These problems require a little bit more review from way back. Let's do one of these together. You guys probably know by now that when you start with an alkane, that there's only really one or two reactions you should be able to do, which is brominate it, okay? And you can brominate with either NBS or Br2. I'll just use Br2, and heat or light, and it selects for tertiary. Okay, so you should definitely know that's the only reaction that we do for alkanes, because alkanes are the most stable of all the functional groups usually. Okay, all right, our goal is to try to get the reactivity over toward this carbon so that we can add a group to it. Okay, so we're starting here with reactivity here because bromine prefers tertiary, but we have to step it over to here. So the way to bridge that reactivity is to make a double bond there. So you need a reagent that will hopefully introduce some kind of a double bond right here. Okay, and then I'm thinking not to worry about the reagents yet, maybe just sort of think if there are a sequence of structures that I can use, like maybe I can put something here that eventually can turn into an alkene, but there's several ways to go with this. You could either make this into a halogen or you can make it into an OH. And I know with OH, because we've been doing a lot of those reactions, that I can oxidize it. And then I know if I have an alkene that I'm trying to make from a carbonyl to an alkene, we just did that reaction up here. Remember? Carbonyl to an alkene, that's the Vidiq reaction. So I want to maybe use a Vidiq reaction to get back to there. All right. So now at this point, I sort of have an idea of what's going to get me from point A to point B. So it's going through this cycle. And now I can free up my mind to think of what reagents it is that I need. I don't want to juggle all that information at the same time. It gets confusing. So right now I'm just going to focus on, I want the Zaitsev alkene. I don't want the alkene up here. I want it here. So I need a small base like sodium hydroxide and heat, or methoxide or ethoxide is fine. Not tert butoxide though. Tert butoxide puts it here at the double bond. Okay. Here what I want is anti-Markovnikov addition of water. Anti-Markovnikov is BH3 in THF. Sometimes B2H6 because borane exists as diborane. I'm going to number these. So 1, 2, 3. Then I also need to do hydroxide in peroxide. Sodium hydroxide is fine. And then step 5 is to oxidize that. Again, I can use PCC or Jones. There's no difference because it's going to a ketone in either case. So I can just put PCC here if I like. And 6 would be figure out the Vidiq you need. I need a 1-carbon Vidiq ylide reagent, PPH3, triphenylphosphine. PH is phenyl, and P is phosphorus. Okay, so that's it. All right. So that's it. I mean, that's a lot of reactions. Okay, this goes back to Chem 261. Chem 262, and now Chem 263. It really is the whole year of OChem right here. So these are great review problems for those, and I will ask you at least one question that might incorporate something from before. So at this point, let's pause it, and then I'll go over the answers with you. All right, for this next one, it's a little tricky where this second carbon is. It could be up here, it could be here. I'm sort of showing an example that's in the answer key, which is that this actually is carbon 2 here, and then you do Markovnikov addition of water to an alkyne that's using HgSO4, H2SO4, and water. And then once you have that, you can apply the Vidiq reaction and then add your OH anti-Markovnikov. That's one way. But, sometimes that doesn't just come to you naturally, probably because you're not thinking about the Vidiq very much right now. So another thing is you might think about adding an OH group here somehow. But if we have that, I'll just play around down here. So if I had gone with the addition of water here, thinking that the OH group could be on the end, so I could reduce that, I'd run into problems trying to get a methyl group attached to this carbon though. So we haven't really learned ways to attach a methyl group here. I'd have to try to get maybe a carbonyl group there and have a methyl Grignard attack, but that would be sort of difficult to do. So because you only have one reactivity center here, and so once you turn that into OH, then you're done. So that hopefully you would get stopped by that right away before you spent too much time on that. So let's fill in the reagents we need for this scheme here. So like I said, step 1, you need HgSO4 followed by, with H2SO4 and water. Okay, this is from Chem 262, alkyne addition of water. And then this next step would be the Vidiq reaction. So CH2, and I'll show the other form of the Vidiq is with the double bond instead of the charges. So CH2 with the triphenylphosphine. And then just anti-Markovnikov addition of water so that you already have your methyl group here. And that's using these reagents here. All right, for the next one, again, we're starting with an alkane, so hopefully you know what to do there. I would think about adding some functionality to that. So I'm thinking bromine group here, or iodine, or chlorine, some kind of leaving group. And we're going to try to get our reactivity from here to here. So I need to consider an elimination reaction. And then I want to add some water here. So I'm probably going to do anti-Markovnikov addition of water. Now I'm almost there, but I have a methyl group here. Can you think how to get a methyl group there? This goes back to our alkylation reactions. So I think what I'll do is I'll oxidize that OH group, and now it's going to be very enticing for methyl Grignard to react there. And then that's it. All right. So our reagents are going to be, so here are the reagents. They're going to be Br2 and heat or light. We get the Br there, or NBS is fine. KOH or NaOH and heat. And then after E2 elimination, we do the anti-Markovnikov addition of water. That's these two steps. And then Jones reagent to oxidize that. Methyl magnesium bromide and acid workup. All right, so if you haven't done the rest yet, let's go ahead and pause it and then check your answer when you're ready. Okay, everyone, so this one is a little tricky. On the bottom, I'm using these hints. So for D, it's oxidative cleavage, and D also requires a protecting group. So let's see here. I'm seeing definitely the bromination here is the first step. Like I said, you have an alkane. That's the only thing you can do to add functionality for now that you've learned. And then here, this is elimination. And I'm thinking when you have a cycle and you open it up, you need to cleave it. So that's what the hint is about. When we cleave it, I think I want to keep it as aldehyde rather than carboxylic acid. So I think I want to use a more mild cleavage agent like ozone with reducing conditions rather than KMNO4. Once I have that, then I'm thinking I have 2 carbonyls and I only want one to react at a time. So I guess I will protect my aldehyde and react the ketone. Then I'll add a methyl group to that ketone, so I end up with this, and then I'll deprotect it and I can add to my aldehyde on the other side. Okay, so here's how I do that. First step is Br2 and heat or light. Second step is NaOH and heat. Third step is oxidative cleavage, ozone, O3, followed by zinc and water, or DMS, dimethyl sulfide. Once you open up this group, you know the aldehyde can be protected since it's more reactive than the ketone. So I'm going to use ethylene glycol in some acid. After that, I'm going to add methyl magnesium bromide as a Grignard agent. And then I'm going to do acid workup to protonate that into an alcohol. That's how I'm going to get this end of it. The H plus is also going to deprotect my aldehyde group. So my aldehyde group will also be ready to go. And I notice I don't have an aldehyde in my product. I need to put a methyl group on it. So I'm going to add another equivalent of methyl magnesium bromide, MEMGBr. And after I work that up, this will be an OH group. So then I need to oxidize it at the very end. So I'll use sodium dichromate, or Jones reagent, or PCC, or KMNO4. All right, so that was a really big problem there. Okay, 10 steps is what I got. Okay, but answers can vary. You can have different, potentially different answers slightly, but this is the way that I believe you should be doing it to use the reactions we've learned so far. Okay, so this one I'm seeing adding an OH. Why? Because I see this is probably from a carbonyl. So I want to turn this into a carbonyl, which is pretty easy. So here I'm going to add the BH3 THF, then peroxide in basic conditions. That's hydroboration oxidation. This step I'm going to oxidize with PCC. I have to use PCC because I want to keep the aldehyde here. I don't want a carboxylic acid. And then this last step is I want to use an amine. This is an imine, so I can just use this whole thing with an H here. So I'm going to use isopropyl amine, which is isopropyl group CH3 CHNH2 CH3. All right, and just a little bit of catalytic acid as well. So this will be shown in the answer key fully, so you can go back and look at that. Here I want to do Friedel-Crafts acylation. So I want to use this carbonyl group with an Cl group and AlCl3 catalyst. That's Friedel-Crafts acylation. I'm going to then Vidiq that reaction right here. Okay, so I'm going to use the same ylid I used up here, CH2 PPH3, this guy right here. Okay, then from there I can just use Br2. And maybe before that step, I want to brominate because this is a meta director here, right? So I want to probably brominate first. So I should have added that there. So let's just say we got this. We're going to brominate while I have a meta director, and then we're going to turn our meta director into the final product by the Vidiq reaction at the very end. This last one, G, is really tricky. You can see that these ethylene groups come from here, these esters. They gave us a hint. We use a protecting group. Ketone is more protective than the reactive than the ester. So our protecting group goes here. So I use ethylene glycol in acid to get this. Ethylene glycol in acid. And then once we have that, then we will also reduce our esters. Sorry, this is ET. Okay, so we're going to reduce our esters into OH groups. Now, OH groups, these look sort of like ethylene glycol already, don't they? So sort of like one equivalent alcohol here and another equivalent here. So that's how we get the acetal in the end. So what I'm going to do is first, after I do this protecting group here, then I want to reduce the esters down using LAH, excess, okay, excess LAH, to get the OH groups here. Then those can attack with catalytic acid, so just a little bit of H+. And that's also going to remove my protecting group here so that the carbonyl is ready to go. Then these guys can attack here after this carbonyl is activated, and we make my acetal with two different alcohol groups, one on this end, one on that end. So that is a little bit strange looking, isn't it? It looks like a bug. Okay, so that's it. All right. So do practice that, and then we'll go over this stuff next.